Hello everyone. What if a solar panel could directly support uh, an electric vehicle's auxiliary system? Something like this. In this video, I will show you a complete photovoltaic MPPT boost converter designed to supply a 48-volt electric vehicle's auxiliary bus, and it is simulated entirely in the MATLAB Simulink. The goal of this project is simple but very powerful. We'll try to extract the maximum power from a solar panel using MPPT. Then we will boost the voltage and supply as a realistic electric vehicle's auxiliary load, uh, all while maintaining the stability and efficiency. So let's start with the system architecture. The photovoltaic array is this photovoltaic array generates DC power based on the irradiance and the temperature. The power is fed into a DC-DC boost converter whose duty cycle is controlled by the Perturb and Observer's MPPT algorithm here. The boosted output supply 48 to 54 volt DC bus, and this is the auxiliary electrical vehicle's auxiliary battery, and it represents the EV's auxiliary power system. Now, firstly, moving into the PV arrays. The PV array model accepts a real physical input where we are giving an irradiance in a watt per square meter and the temperature in the degree Celsius here. And in this simulation, the irradiance is set to 1000 and the temperature is 25 degrees Celsius, representing a standard test condition. The PV voltage and the current are measured in the real time, or instantaneous voltage and current are measured and power is measured here. Okay, in case of a PV array, we have calculated and found that we require two strings of PV arrays which are connected in series, and the module I have selected is A10 green technology 220 watt, so it will produce a maximum power of 219.876, so approximately 220 watt. And then cells per module is 60, number of cells per module is 60. Open circuit voltage is 36.06 and short circuit current is 7.97, and the maximum power point voltage is 30.12. Then current at the maximum power point is 7.3, and temperature coefficient and temperature coefficient at short circuit is given here. Similarly, we have can plot you here, and the current, as I have mentioned earlier, the current is at maximum is 7.3, and the power at 25, and the power by voltage and the current by voltage. So your MPPT values are given here. Okay, this is a standard test condition. And let's run this value. So when I simulate this model, firstly, why do we use the boost converter here? Boost converter requires inductor coil, then it is connected to a diode in series, and capacitor is connected in parallel to the load. And we have a IGBT or MOSFET, which is controlled, whose switching is controlled by the pulse or the PWM generator. And in order to generate the pulse, we have an MPPT algorithm here, and it is compared with the repeating sequence, and the MPPT controller produces the duty cycle, and by comparing it, we produce a pulse. This pulse is used to control the switching of the boost converter. Why do we use the boost converter? The boost converter is used because the PV voltage generated is just 32.63 volt, and what we require is 48 to at the output voltage, 48 to 54 volt is required. Therefore, since the PV is not able to generate the 48 to 54 volt, we are using the boost converter to boost the low PV voltage, and the PV operates around 32.63 volt, while the auxiliary bus operates at 54 volts. So the boost converter is not only steps up the voltage but also control the PV operating point by adjusting the duty cycle. Now, in case of the MPPT algorithm here, the head of the system is a Perturb Observe MPPT algorithm, and at each control step, the algorithm measures the PV voltage and current and calculate the PV power. Then, if a small change in the duty cycle increases the power, then the algorithm continues in that direction. If the power decreases, the perturbation direction is reversed. Over time, this process forces the PV array to operate near its maximum power point. I have written all the descriptions here, so it's very clear when you go through the code. Now, in case of the duty cycle, I am getting around 0.338, and the MPPT algorithm outputs a duty cycle between 0 to 1. This duty cycle is between 0 to 1, and this duty cycle is compared with the high frequency carrier signal to generate this pulse. These pulses drive the IGBT switch, and inductor and capacitance values are calculated and given here. From the load and EV relevance, I would say that my load is, in case of resistance, it comes around 7.5 volt. The output side, the DC resistive load represents an EV auxiliary system. So electric vehicles auxiliary system is represented by this battery, and this battery is used to power the cooling pump, your dashboard electronics, and other lot of accessories, lighting systems, and you do not have to rely on the main battery system of the electric vehicle. Mm, On the output side, the current is 7.143 and voltage is 53.75. So we are getting around 391, while 383 watt here at the output side, and the input or the solar PV array generates 391 watt. The overall system efficiency is calculated as output power divided by input power, so we get around 98%. The remaining losses are attributed to switching losses, diode conduction, and inductor resistance losses. Now this confirms that now to validate the model, we have a MPPT that produces the duty cycle, and it helps to boost the 32.63 volt to 53.57 volt, which is an operating auxiliary PV battery. Why this model is realistic? Our model represents a realistic solar assisted EV auxiliary power system. It demonstrates how the renewable energy, and power electronics and the control algorithm can work together in a modern electric vehicle. And in further moving into the further outputs, we can bring the some improvements in the model, that is by adding the 48 battery with CC or CP charging controls using a real solar irradiance data instead of going with the standard condition like 1000 irradiance and 24 degrees Celsius. We can bring some solar irradiance data and temperature data and conduct the realistic analysis here. Okay, I have output results here, where yellow is your voltage and current is red. During the startup, the MPPT controller intentionally perturbs the duty cycle to locate the maximum power point. This causes the temporary voltage and current oscillation. Then after that, once convergence is achieved, the DC voltage and the current is stable, and look at here, it is stable. Current is also stable, and this behavior confirms a stable closed loop operation and correct implementation of MPPT algorithms. At starting, there is some oscillation because of the perturbation duty cycle. So I will be uploading this complete MATLAB Simulink model, then MPPT source code, and all the related technical documents, calculations, and the assist report. You will be able to download the full simulation file, study the block level implementation, modify parameters, and reuse this model for learning for your academic projects or for the researchers. Please go through the description links. I will put the video, the Gumroad link in the video description, and you can also check my bio for other Simulink or MATLAB project models. Thank you, and please do not forget to like, share, and comment.